Good morning, everyone. Welcome to Statics. Today we are starting chapter 8, titled as Friction. Okay, so if you remember, we are done with chapter 6. We did the force analysis of truss systems. We did two methods. So now we are starting with friction. So we all know what is friction, right? So whenever we are moving one body, one material against some other material, so there is some resistance between those two materials, and that is called friction, right? So we all are aware of the meaning of friction and why do we have friction. So even if you rub your hands against each other, so you can feel some friction between your two hands, right? So whenever we are trying to move one material against other material, we'll have some kind of resistance between those two materials, and that is called friction. Okay, so if you just look at this picture on your screen, so what's going on here? So there's a man, this guy is trying to pull a box, right, with a rope. So he's applying some force, right, towards him to trying to move this box, right? So as he's trying to move this box, now this box is placed on the ground, on some surface, right? So again, we have two materials in contact. One material is the box and one material is the surface. Maybe the ground surface, maybe floor, maybe any surface, maybe on the table, right? So now we have two materials in contact with each other, and this guy is trying to pull this box, so he's trying to move this box against this surface. So that's why this is the friction force which is developed between these two surfaces, right? So this is the main concept of friction. We'll go ahead and we'll see what are we covering in today's lecture. Okay, so let's talk about the application. In this picture, you are well familiar of the brake system of maybe your bike, maybe or any other vehicle, maybe a car or anything. So we use brake systems to stop the car, to stop the bike, bicycle, or any other vehicle, right? So now it's important to understand the frictional forces involved, right? You push this rubber pad against the wheel, right, rim of the wheel, to stop the bike, right? So why does the this wheel stops? Because of the friction, right? So you need to understand what are the forces acting once two objects or two materials are in contact with each other, right? So that's what's happening once we have friction between these two materials or any two materials, right? So now we will be talking about, in section 8.1 of your book, we'll be talking about characteristics of dry friction, right? So why we call dry friction? Because once there's no lubricant, there's no liquid, there's no lubricant between the two materials, right? So then we call it a dry friction. And there is wet friction, but we will study the wet friction in some other course, maybe the fluid mechanics course, right? So in this course, we are only talking about dry friction. Okay. Now, as you can see on the left side in this picture, again, there's a box placed on some surface, maybe a floor. So now, what are the forces acting once this box is placed on the floor, right? So first of all, let's read this. Friction is the force of resistance acting on a body which prevents or resists the slipping of a body relative to a second body. So as we just discussed, that once two materials, two bodies are in contact and you're trying to move one body relative to the other body or other material, then there's a resistance force which is called friction, right? So in this case, if you see, now this is the weight of this box, right? Acting vertically downwards through the centroid or center of gravity of this box. Now this is the applied force P, which is being applied to move this box against this surface, right? So these two forces are acting on this block, the weight of the block and the force P, which is applied, the external force. Okay, now what about the frictional forces? So as we know that frictional forces develop between the two surfaces, right? So what are the two surfaces? One is this block surface or this material, and one is this floor, right? So these are the two surfaces or two materials, right? So they are in contact at this point, right, along this surface. Okay, so where's the friction force? This is your friction force, this guy, right? So this is your friction force. Now, main thing to note and to remember is that friction force always acts against or opposite to the direction of motion, right? So if you see, the force P is applied to the right side, right? Positive x direction. So the friction force will be in the negative x direction or opposite to force P, because force P is trying to move this box in positive x direction. So friction force will be in this direction, right? Negative x direction. So that is your friction force. Okay. Then we know that we have the weight of the block acting downwards, right? So there is, whenever there's a weight of the body and the body is placed on some floor or some surface, then we have a normal force, right? So now this is the normal force which is acting upwards, because weight is acting downwards, so this is acting upward. This is the normal force, this guy. Normal force acting upwards. Now in this case, the normal force, the distribution is not a rectangle, it's like this. So this is the distribution of the normal force, right, along the surface of contact between these two materials. Okay. Now, if you look with your own eye, you'll say, okay, these two surfaces are plane. But if you look through microscope, so at the micro level, these two surfaces are not really smooth, not really plane, right? There are some undulations between the two surfaces, right? So if you look through microscope, you'll find the surface like this, right? Both the surfaces, the top surface, which is the box, and the bottom surface, which is the floor. Right? So there are some undulations between those two surfaces. So there are some gaps and some contact points. So the normal force and the friction force both are being applied at those contact points, right? So as you can see here, let's start from here. So this is, let's say, delta L1. So delta N1, and this is your delta F1. So delta F1, delta F2, delta F3 goes up to delta Fn, right? So the increments of the friction force, and similarly increments of the normal force, delta N1, delta N2, delta N3. Now if you want to make a resultant out of this friction force and normal force, you'll have this guy, this guy, this guy, this guy. Let's call it delta R. So delta R1, delta R2 goes up to delta Rn, right? So that is the resultant of the friction force and the normal force. Okay. So we already talked about that frictional force acts parallel to the contacting surface in a direction opposing the relative motion or tendency for motion, right? So we already talked about that. Now, for the body shown in the figure to be in equilibrium, the following must be true. Now we already know this, that this is the box, or this is the block with a weight of W. The normal force N is acting upwards at a distance x from the center of gravity, because the normal force distribution is not rectangle, right? So it's not evenly distributed, so it's like a triangle. So that's why the resultant normal force x at this point at a distance x from the center of gravity, right? So this is distance x. Okay, now at the same point we have this friction force, this guy, right? Friction force acting opposite to direction of motion, or opposite to the direction of applied force, which is force P applied here, right? So now this is the free body diagram of this block resting on this surface. Now, for this box to be in equilibrium, what condition should we have? So let's say this is point O, this guy, this point O, this point. So let's take moment at this point. And why at this point? Because we have two forces acting at this point, F and M, and they will go to zero once we take moments at this point, right? So once the body is in equilibrium, then moment at any point should be zero, right? So let's take moment at point O. So if we take moment at point O, what do we get? F equals P, N equals W, right? So F equals P, this guy and this guy, they should be equal. N equals W, this guy, N equals W, and W times X equals P times H. So W times X, the moment of the weight on about point O, and the moment of P about point O. So that should be equal. So this condition, right? So if these conditions are there, then we'll say that, okay, this box or this body is in equilibrium. Okay, so now we know how to apply the friction force when we have a problem having two materials in contact or two bodies in contact. Okay, so let's move forward. Now let's see some more on dry friction. Okay, so this is the same box which we already discussed, with a weight of W, force P being applied. Now this is the free body diagram. This is the weight acting on center of gravity. This is the force P acting rightwards, trying to move the box. This is the friction force F. This is the normal force acting upwards at a distance x from the center of gravity, right? So we have all these forces acting. Now, if we draw a plot between the force P, which is the applied force, and the force F, which is the friction force. So if we draw a plot, we'll get something like this. So this is the plot showing the relation between P and F, the applied force and the friction force. Now, as you can see, the initial portion of this curve is linear up till this point, right? So in this region, P equals F, because it's a linear curve, right? So P equals F. Now, what do we mean by P equals F? With P equals F, you don't have any motion. The block doesn't move, right? Because the applied force equals the friction force, right? So there's no balanced force to move the box, right? So that's why we'll say this is a no motion zone. Now, what about this point? At this point, we call it impending motion point, right? Now, if the force P increases from this point onwards, then there will be some motion. So that's why this point is called impending motion. Impending motion point, right? So this is impending motion. Now, once you increase the applied force from this point onwards, then there's a decrease in friction force. As you can see with this plot coming down, this line, this curve coming down, that there's a decrease in friction force. Now, once P increases and friction force decreases, then the block moves. So that's why we call it the motion zone. Beyond this impending motion point, there is a motion zone of this system, right? So that's how this block moves once we increase the P beyond this impending motion point. So then it keeps on moving. Okay. Now let's talk about this impending motion point. So at this impending motion point, the force is called Fs. We call it Fs. This guy. So this is Fs, the static friction force. And once we are in this range, the motion range, then we call it Fk, which is the kinetic friction force, right? So static friction force is until we have no motion or until the impending motion point. And after impending motion point, we have Fk, which is the kinetic friction force, right? So that's how we can explain this plot. And let's see what's given here. To study the characteristics of the friction force F, let us gradually increase the magnitude of the force P, which we already discussed. Typically, experiments show that the friction force F varies with P as shown in the right figure above. So we already talked about this. We already talked about the changes in friction force with respect to the applied force P, right? Okay, so let's move forward. Okay, we already talked about this, but let's just quickly go over it again. The maximum friction force is attained just before the block begins to move, right? So we already talked about this at this point, right? This is the impending motion point, right? Once the friction force is maximum and just before the block begins to move, right? So at this point, we have this relation between normal force and friction force. Fs equals mu s times n. Now, what is mu s? This guy, mu s is the coefficient of static friction, right? And the value of mu s depends on the two materials in contact, right? So that's how we have this relation between the friction force or static friction force and the coefficient of static friction and the normal force. So just remember that mu s, this guy, is coefficient of static friction because we are in the no motion zone here. So that's why we call it static friction and coefficient of static friction, right? And this diagram, we already discussed about this. This is the block, this is the weight of the block acting downwards, the normal force acting upwards at a distance x from the center of gravity. This is the force F, Fs, which is the static friction force. Now at the impending motion point, we have this equation. Fs equals mu s times normal force, right? So this is about the no motion zone. Now, once we are in this motion zone, once the block starts moving, as it's written here, once the block begins to move, the frictional force typically drops. So as we saw earlier, and in this plot also, friction force comes down, right? So the friction force started to decrease. And that's why we have the movement of the block, right? So the friction force typically drops and is given by this guy, this equation, Fk equals mu k times n. Now, as we discussed earlier, this is the motion zone or the kinetic zone. So that's why we call it F sub K, which is the friction force or kinetic friction force. And this guy, mu sub K, is the coefficient of kinetic friction. Now, you can just visualize then that mu K, or the coefficient of kinetic friction, is less than the coefficient of static friction, right? And Fk is also less than Fs, right? So as it's clear from this these diagrams also, right? So that's how we can you know, we discussed about different concepts which involving the dry friction, right? Movement of two surfaces in contact. Okay. Now, how to determine mu s, or coefficient of static friction, experimentally, right? So again, let's take the same example of the block with a weight W, the force P applied to the block. Now, if the block just begins to slip, right? So what that means, we are at the impending motion point, right? So the maximum friction force, Fs, equals mu s times n, this guy, right? So we already saw this earlier. Now, mu s is the coefficient of static friction. We already talked about this. Now, when the block is on the verge of sliding, again, the impending motion, this point, impending motion, and the normal force and the friction force Fs combine to create a resultant Rs. As we discussed a couple of slides earlier, that we have this guy, the static friction force, this is the normal force, and this is the resultant force, let's say Rs, resultant force of this friction force and the normal force, right? Because they are acting at one point, right? So let's make a resultant out of these two forces. Now, from this figure, let's call it this angle, let's call it phi s, right? So now from this figure, we can see that tangent of phi s equals Fs divided by n, right? But we know that Fs equals mu s n, so we'll put that here, and we get tangent phi s equals mu s, right? So that's how we can find the static friction coefficient. Okay. Now, let's do a little experiment to find mu s, or coefficient of static friction. How can we find the static friction coefficient in the lab? So now a block with weight W is placed on an inclined plane. So let's say this is an inclined plane, inclined with some angle, let's say theta s, to the horizontal, and we have this block placed on this inclined plane, right? So the plane is slowly tilted until the block just begins to slip, right? So we increase this angle, theta s, this guy, so that we can see this block or this box to move. Okay, so once we do that, what do we get? The inclination theta s is noted at the point where the block begins to move, right? So the analysis of the block just before it begins to move, what it gives us, right? So let's make a free body diagram first. So this is the block, this guy is the block, same block. Let's draw a free body diagram. We have weight W acting downwards. We have this guy, normal force acting perpendicular, normal to the surface on which this block is placed. What else? We have this guy, Fs, which equals mu s times n. So that is the friction force, right? Because the block is moving in this direction, right? So that's why friction force is in this direction. Okay, so that's this is the free body diagram. Now, let's talk about, let's apply equations of equilibrium. Let's apply sigma Fy equals 0. This is taken in this direction because we are taking this as our coordinate axis. Let's take this as y, this is x. Okay, so this, that's why we are taking sigma Fy in the y direction. And if you do that, what forces do we have in y direction? So we have this normal force N, this guy, and the y component of the weight, right? So that's why we have N minus W cosine of theta s, because this is your theta s, this guy, right? So the y component will be W cosine theta. Okay, so equals to 0. This is our sigma Fy. Now sigma Fx in the x direction, sigma Fx equals to 0. What forces do we have in x direction? So we have Fs, which we know equals to mu Sn. So this guy, and it's in the positive x direction. So let's take it positive. And then we have one force in the negative x direction, which is the x component of the weight, or we have negative W sine theta s, right, equals to 0. So these are the two equations which we get from this free body diagram. Now using these two equations, what we get? We get this mu s equals W sine theta divided by W cosine theta, which amounts to tangent of theta s, right? So again, we get mu s equals tangent of theta s. So the simple experiment allows us to find the coefficient of static friction between two materials in contact, right? So that's how we can find the value of mu s in the lab, right? So just by this guy, that mu s equals tangent of theta s. So this allows us to find the value of coefficient of static friction. Okay, now let's talk about problem solving. We know that it's a major part that we talk about the concepts, and then we do some problems, and we get problems to solve in the exam, in the quizzes, and the homeworks. Okay, so let's talk about problem solving. So what are the steps for solving equilibrium problems involving dry friction? Okay, so first step, draw necessary free body diagrams as we did on the last slide. First, we made a free body diagram of that box, right? So make sure that you show the friction force in the correct direction. It always opposes the motion or impending motion. So just make sure that we remember the friction force is always opposite to the applied force or the direction of motion, right? So that's one most important point that we need to remember. Okay, then determine the number of unknowns. Do not assume that F equals mu s times n unless the impending motion condition is given, right? So this is really important because we know that once we are at impending motion point, only then F equals mu s times n, right? So if this condition is given, that there is impending motion condition, only then we can apply this, otherwise we cannot, right? Okay, so now we know the unknowns. Now we can apply the equations of equilibrium and appropriate frictional equations to solve for the unknowns, right? So this is how we are done with, we can solve any problem involving friction. Okay, now with this, we come to the end of the theory portion of today's lecture. Now let's solve a problem involving friction. Okay, so let's look at the statement. A car has a mass of 2000 kilogram and mu s equals 0.3. Mu s, we all know that it is coefficient of static friction. So this mu s is given, the mass is given 2000 kilogram. Now what we need to find, we need to find the smallest magnitude of force F required to move the car. So this force F, which is being applied, so we need the smallest magnitude of this force to move the car. If the back brakes are locked, so the brakes at this point B, the back brakes, they are locked, and the front wheels are free to roll, right? Okay, so this is the statement. Now we can see the car on the left side of the screen with the center of gravity here. So the weight of the car will be acting at this point, right? And then we have these wheels, and the other dimensions they are given, and the force F is being applied at an angle of 30 degrees from the horizontal at point C, right? Okay, so this is the thing. Now, what we are going to do? What we are going to do, let's see the steps. Draw the free body diagram of the car. We all know that we need to make the free body diagram. Then determine the unknowns. So what are the unknowns? How many unknowns do we have, right? Then apply the equations of equilibrium and friction equations to solve for the unknowns, right? So we'll apply the appropriate equations of equilibrium and friction equations because we have friction involved in this form, right? So that's why we have this coefficient of static friction given. And why there's friction? Because the back wheels are locked. So once the force F is applied, then there'll be friction between these back wheels and the ground surface or the road, right? Okay. Now, first of all, let's make a free body diagram. So on the right side, you can see the free body diagram. Now, what are the forces acting on this car? First of all, we have this mass or the weight of this car acting downwards, right? At this point, which is the center of gravity, right? So 2000 kilogram was the mass times 9.81 will get the weight of this car, right? So this is W. Okay, then this is the force being applied, the external force, which is being applied at 30 degrees to the horizontal. Okay, so this is being applied at this point C. Now the dimensions are given. We are not talking about the dimensions. You can already see these dimensions. Now, there's a normal force acting at point A, right? So let's call it N sub A, this guy. This is normal force from the front wheels. Now there's no friction force at the front wheels. Why? Because these front wheels are not locked, right? So they can just roll. So there's no friction between the road and these wheels. Now back wheels, they are locked. So once the force F is applied, then there'll be some friction, which is, let's say, F sub B between the wheels and the road, right? And again, the normal force between the wheels and the road is, let's say, N sub B. So now these all are, are all the forces which are acting on this car. So now we are done with the free body diagram. Now let's see how many unknowns do we have, right? So we have F, NA, NB, and FB. So we have 1, 2, 3, and 4. So we have 4 unknowns, right? Okay. So there are 4 unknowns: F, NA, NB, and FB, right? Okay. Now let's apply equations of equilibrium first. Okay. So you know that we can apply sigma fx, sigma fy, and sigma moments. So let's apply sigma fx. So how many forces do we have in x direction? So we know that we have FB, which is in X direction. So let's put FB here. What else? Now we also have this. Let's this is Fy. This is Fx, right? So we have this Fx, the x component of the force F in X direction or negative X direction, right? So that's why we have this negative F cosine of 30, right? So this is our equation for sigma Fx, Fb minus F times cosine of 30 equals to 0. So let's call it equation 1. Okay. Now, let's apply sigma Fy with positive upward sign convention. So let's apply this guy, sigma Fy equals to 0. Now, what are the forces acting in y direction? There are too many forces, right? First of all, if you start from the left side, we have Fy, the y component of the force F, right? Which is F times sine of 30. Then we have n sub a, this guy, again acting upward, so positive. Then we have n sub b, which is again positive, the normal force at point B. Then we have the weight acting downwards, right? So which is 2000 times 9.81, which will give you 19,620, right? So this is 19,620 newtons equals to 0. So this is, let's call it equation 2, right? So now we got these two equations, but we have 4 unknowns, so we at least need 4 equations, right? So let's apply moments. So let's apply moments at point A, right? So if we take moments at point A equals to 0 with the sign convention of counterclockwise positive, now how many moments we are getting at point A, right? So only an A would not create any moment, so there's no moment from n sub A. Now there is moment from Fx, Fy, there's moment from W, there's moment from n sub B, and there's no moment from FB, right? Because that is also passing through point A. Okay, so we have these 4 moments. So F cosine 30 times 0.3, this is the X component of F creating moment, counterclockwise moment at point A. So 0.3 is the moment arm. Then the Y component creating a clockwise moment. So Fy is creating a clockwise moment, and the moment arm is 0.75. Then we have counterclockwise moment from n sub B, and the moment arm is 2.5 meters. So we get this. Then we have the clockwise moment from the weight, and the moment arm is 1 meters, right? So that's why we get this, okay, equals to 0. So this is your third equation. So now we have 3 equations, but since we have 4 unknowns, so we need 1 more equation. And also there's some friction going on at point B, so we can apply the friction equation, right? So just assume that the real wheels are on the verge of slip. So what is that point? That's the impending motion point, right? So once we know that, once we have the impending motion, then we can write this equation. F sub B equals mu s times n sub B, right? So we can write this equation for the friction between the wheels, the back wheels, and the road, right? And we already have the value of mu s, which is 0.3. So we get Fb equals 0.3 times n sub B. So this is our equation 4. So now we have 4 equations, 3 from the equations of equilibrium and 1 from the friction equation. So now we have 4 equations and we have 4 unknowns, right? So now we can solve these 4 equations to get the values of these 4 unknowns. So now I'm not going to go into the details of solving these 4 equations, 1, 2, 3, and 4. So if you just solve these 4 equations, you get these answers. So you get F equals 2,762 newtons, this guy, and also NA, NB, and FB. But the main thing is F, which is 2,762 newtons, right? So if you go back, if you look at what was required, so we were to find the smallest magnitude of force F required to move the car if the back brakes are locked and the front wheels are free to roll, right? So this is what we have found here. F equals 2,762 newtons. If we apply this force, then the car will start moving, right? So just after the point of impending motion. All right, so with this, we come to the end of today's lecture, and we'll see you in the next lecture. Thank you.